Sometimes the most interesting questions aren't the ones you find in a textbook. They come from someone just being genuinely curious. And that's exactly what happened here. This whole explainer was sparked by a simple question on a math forum that gets right to the heart of a formula a lot of us just memorized, but maybe never really truly understood. So, this user on Reddit, luciferx_6, asked this fantastic question about parabolas. Why is it always this specific formula? And it turns out the answer is just this beautiful showcase of how interconnected math really is. So today, we're going to unlock that secret, and we're going to do it by looking at it from 3 totally different angles. Okay, so before we can really dig into why the formula works, we got to make sure we're all on the same page. So let's do a super quick refresh on the main characters in this story, the parabola itself, and its most important feature, the axis of symmetry. First up, the parabola, right? It's that classic U-shaped curve that you get anytime you graph a quadratic function. That equation, y equals ax squared plus bx plus c, that's like its DNA. The a, b, and c are what tell the curve how to form, where to sit, and which way to open. And what's its most important quality? Well, you're looking at it. A parabola is perfectly symmetrical. Whether it opens up like this one or opens down, it's a perfect mirror image of itself. And that idea, that symmetry, is the absolute key to everything we're about to do. So, that imaginary mirror line, that's our axis of symmetry. It's just a vertical line that slices the parabola right down the middle into 2 identical halves. And it always passes through that one special point, the very bottom or the very top, which we call the vertex. Our mission today is to prove why the equation for that line is always x equals negative b over 2a. All right, let's jump into our first method. I like to think of this as the power tool approach. If you've got a little calculus in your back pocket, this is by far the fastest and most direct way to get our answer. The big idea here is actually really simple. The vertex, right, is the very peak of the hill or the bottom of the valley. It's the one and only spot on that whole curve where, for just a split second, the slope is perfectly flat. It's 0. And since calculus is basically the science of slopes, we can use it to pinpoint that exact spot. And here's how it works. It's pretty elegant, actually. You take the standard function, and you find its derivative, which gives you a new formula for the slope at any point, 2ax plus b. Since we want the point where the slope is 0, we just set that equal to 0. A little bit of high school algebra, subtract b from both sides, divide by 2a, and boom, there it is. We found our x, and it's negative b over 2a. So clean, so efficient. But hey, what if calculus isn't your jam? Or maybe you just haven't looked at it in years. No problem at all. Let's try a totally different path, one that's much more visual and geometric. We're just going to use the parabola's own symmetry against it. Okay, so by its very definition, that axis of symmetry has to be smack dab in the middle of any 2 points that are at the same height. And what are the easiest, most convenient points to use? Well, the roots, the 2 spots where the parabola hits the x-axis, because of course, they both have the exact same height, 0. And what's our go-to tool for finding those roots? Ah, yes, the legendary quadratic formula. Now, just look at the formulas for the 2 roots. They are almost identical. The only thing that's different is that one adds that square root part and the other subtracts it. That plus minus is the secret sauce. That's the symmetry right there in the formula. So, to find the point that's exactly in the middle of the 2 roots, all we have to do is average them. And here's the magic. When you add them together, that plus square root part and that minus square root part, they just completely cancel each other out. Poof! All the complicated stuff vanishes, and we're left with something incredibly simple that cleans right up to, you guessed it, x equals negative b over 2a. This graph really makes the idea click. Look at the points negative 1, 3 and 1, 3. They're at the same height, right? They're mirror images, so the axis of symmetry has to be the vertical line exactly between them. And what's the average of negative 1 and 1? It's 0. So the axis of symmetry is x equals 0. It's just that intuitive. Okay, 2 proofs down, 1 to go. And for our third and final path, we're going to use pure algebra. There's no slopes, no roots, just good old-fashioned rearranging the equation until it confesses and reveals the secret of its own vertex. This clever technique is called completing the square. And the entire goal here is to take our standard quadratic equation and just rustle it into a different shape. We want to rewrite it in something called vertex form.
And why on earth would we do that? Because vertex form is specifically designed to just hand you the coordinates of the vertex on a silver platter. Just look at the two forms next to each other. On the left is our standard form, but look at the one on the right, the vertex form. The coordinates of the vertex are literally built right into the equation. They're just sitting there as h and k. So if we can just change our equation from the standard form to the vertex form, that h value will be the x-coordinate we've been hunting for all this time.
Now, I know the algebra here might look a little intense, but don't worry about memorizing the steps. Just follow the main idea. We are just strategically rearranging the pieces of the standard formula. The key move is in the middle, where we create that perfect square. And once we get the equation into that final vertex form, we can just see that the term x plus b over 2a is sitting in the exact same spot as x minus h was. Well, that can only mean one thing. H has to be equal to negative b over 2a. The answer just appears right out of the algebra itself.
You know, this comment from Isotope X in that original thread just perfectly captures the feeling, doesn't it? It's not really just about getting the answer. It's about seeing that there are so many cool and different ways to get there. So let's step back for a second and bring this all together. What is so cool about this whole thing isn't just the formula itself, but the fact that we proved it's true in 3 completely independent ways. Think about it. We took 3 totally different roads. We used the slopes and derivatives of calculus. We used the visual symmetry and midpoints of geometry. And we used the pure symbolic manipulation of algebra. Each path started from a different idea and used different tools, but every single one of them led us to the exact same truth: x equals negative b over 2a. And this brings us right back to our original poster, Lucifer X_6, who I think summed it up perfectly. This is why math is so amazing. It doesn't matter which way you choose to go. If your logic is solid and you do it right, you will always arrive at the truth. It's reliable. When you get right down to it, this one little formula is like a crossroads, a meeting point for calculus, geometry, and algebra. And it just makes you wonder, doesn't it? What other amazing, elegant truths and hidden connections are just sitting there waiting to be discovered in the math we think we already know?